Hello, and my name is Lolita Diaram, and this is an analysis of different white noise waveforms using digital sampling techniques for the AE 2610 class. So first, some context. In the background, sound-to-data conversion is a widely applicable concept, especially within engineering. Digital sampling tools are really important to understand issues within aircraft, as sometimes you can't actually see what's going on, and audio has to be used to figure out what are the mechanical issues. So analyzing sound waves using live feeds and digital data acquisition are real-life techniques that engineers use to solve problems. And these are the objectives right here, as referenced in the lab data manual. So in this experiment, we were instructed to create our own experiment using sample audios. So I chose to study the waveforms and data generated by 10 different white noise tracks that are pre-programmed onto a star projector that I have in my room. And I often listen to these while studying. After doing some tests with sample audios, I hypothesized that more melodic sounds will have lesser deviation and some sort of sine wave, while white noises will vary. So we'll see if that actually proves true. So the significance of this experiment is that we can help discern what makes some noises more pleasant than others on a scientific basis, and this can lead to further study on music and scientific waveform analysis. So for the approach, I used the LabJack T4 digital sampling kit and the other items that were provided. For the experiment, I first calibrated the system using a tone generator and found the data of sound waves. Then I went through the 10 white noise sounds, and the raw video of that will be linked in the description. So the data collected is the live waveforms and the captures of the graph. The numerical values were only used for validation. So this is for the calibration, a short video, so of the sine waves. And for the results, these were the different tone tests of simple sine waves at different hertz, then the square wave, sawtooth wave, and triangle wave. So the observations, qualitatively, the sounds with the square and sawtooth waveform, they sounded more mechanical and a bit less pleasant, whereas the sine and triangle both sounded humming and a bit more pleasant. And these are some other observations. So these are the captures of the actual experimental audio. So the first sound was a constellation tune, and it looks like a somewhat noisy sine wave or triangle wave, which is as I predicted. And it also has a low power spectrum range with a little bump right here. For the second one, it was a hopeful cosmic melody, and it seems somewhat like a triangle wave with a lower power spectrum range. So both of these are in line as expected with more of a humming and less harsh noise, so it is a triangle and a sine wave. And the first two sounds also have less background noise, so this register is also accurately reflected in the graph. For sound 3, it is a tropical forest white noise, so you can see the noise is reflected in the triangle waveform, and there's not as much deviation up here. You can see the noise up here is kind of reflective of the noisiness of the sound, but it is a pretty clear triangle wave. For the water flowing, so this was an interesting one. I hypothesized that it would be a product of sines, and it's somewhat interesting to see it's like a sum and a product simultaneously. You can see the range right here indicates it's a bit more noisier in the background, but it is on a lower register. Sound 5, and you can see the x-axis is adjusted to see the waveform shape right here. So sound 5 is the beach waves crashing. So you can see similar elements to the water in the previous one, but there is a bit more of a high spike because of the crashing, which is a bit more harsh. Sound 6 is white noise that is similar to a cruising airplane. So it's at a very high frequency and a bit more random, and you can see the noise is down here. It's a bit more difficult to identify, so I blew it up a bit. And in the zoomed in version, you can see that it looks roughly like a product of sines. For the campfire crackling sound, it's way more randomized, and during the crackles and pops, it looks more like a sawtooth wave, whereas the others are square and sine waves, or triangle waves. The driving on a gravel road, you can see here that the noise is a bit more constant, and there are some gravel crunches where you can see in the areas right here it's a bit louder, and the registry is also somewhat similar to white noise. Sound 9 is the thunderstorm, so you can see it looks like a triangle or sine wave combo, and the thunder, which isn't shown in this capture, is also like a sawtooth wave, which makes sense because it's a harsher sound. And during the thunder, there is also a spike near the 6,000 at the power spectrum because it is louder. And the last sound is the high-pitched small creak. So again, you can see it's like water, and the shape is almost similar to the forest sound with the triangle wave and the deviations. And you can see the power spectrum spikes in the lower register with a somewhat noisy variation throughout. However, you can also see elements of the beach wave crashing and the flowing water of sounds 4 and 5, which is really interesting to see that the waters are somewhat similar. The full video will be in the description with included timestamps, but unfortunately the video file for the second half didn't quite work, so I used a backup video there. Uh, However, you can hear the audio throughout, so that might be helpful to refer to if you wanted to go through and see the actual experiment. So for the conclusions, because of this experiment, we're now able to identify the key digital aspects of very common white noise audios. The more noisy audios did have a higher power spectrum range, whereas the more melodic audios had a lower spectrum range and were triangle or sine wave shapes. Abrupt and harsh noises were exhibited as square and sawtooth waves, and all of these are within expectations. Lastly, my hypothesis was somewhat correct. The water noises are in fact a sine wave. So some future questions that we can go from this experiment is, would a bass heavy tune be registered as a low frequency sine or triangle wave? Would a bass boosted track create new frequencies that weren't present in the original? And how can we use specific observable frequency and power spectrum differences to maybe reverse engineer edited tracks, apply similar effects on other tracks, and maybe even create a piece of music without ever looking at it, just by using power spectrum? It might be a cool challenge to do in the future. These were my references, and thank you.